Hi everyone, it's my pleasure to talk to you today about electric road systems for decarbonising heavy goods vehicles in the UK, and in particular I'm going to talk about the impact that ERS can have on reducing the required battery size requirements for future electric trucks. For those of you not familiar with the system, an electric road system is a system comprising either overhead cables or some sort of in-road conductor which enables vehicles, including heavy goods vehicles, to charge dynamically whilst in motion and also to draw traction power from the system. And some early work done a couple of years ago showed that this kind of setup is very economically attractive for decarbonising HGVs in the UK versus competing options of what we call big battery electric trucks or hydrogen fuel cell electric trucks. And one of the big benefits of ERS is that it reduces the overall battery capacities needed for many typical journeys versus the big battery reference case. And this has a number of benefits, including reducing vehicle cost, reducing vehicle weight, and hence the overall efficiency of the vehicle and of the fleet, and of course embodied emissions associated with the production of the battery packs, but also all the resources required in the production of those battery packs. So in this work, what we set out to do was to look at some real UK logistics journeys across several charging scenarios of both ERS and static charging, and to investigate and quantify the exact impact that ERS can have on reducing those required battery sizes. This brings me to our simulation model, which we used to analyze this. The first part of the model is what we've called the drive cycle generator. So this is taking the definition of your route in terms of origin, destination, and any stops in between, defining where charging is available, both from an ERS and a static charging perspective, and running this through the generator to output a target speed profile, an elevation profile, and charging profiles, kind of saying where the vehicle has access to charging and is charging at what kind of rate. And this generator makes use of the Here Maps API, and it takes into account things like posted speed limits, stops, traffic lights, roundabouts, all that sort of thing. So this is then fed into the second part of the model, which is the vehicle model, which was created in consultation with some of our industry partners at Scania to be as representative as possible of future e-trucks. And what we get out of this at the end of the day is a fully characterized drive cycle, fully characterized power and energy consumption profiles, and importantly, we get an understanding of what the battery state of charge would be doing throughout that journey. More specifically, we actually look at what's called the battery dip, which is a way to look at how much battery would have been required without knowing the installed battery capacity to start off with. Just a few more other points on the simulation model. So firstly, this was built off of an existing electric bus model, which was then updated in consultation with our industry partners at Scania and Siemens. And we were able to get some data from the German ERS trial. We ran a validation over a 35-kilometer journey segment, and we obtained just over a 1% error in terms of energy consumption. So we're quite confident in the accuracy of the model. The model includes regenerative braking. We've assumed a usable state of charge of the battery of 20 to 100%, so a range of 80%. And we've been conservative and assumed the maximum permitted combination mass of 44 tons throughout the journeys. We've also included additional possible loads on the battery, such as cabin heating, trailer refrigeration. And from a charging perspective, we've assumed that from the pantograph, we can charge the battery at around 150 kilowatts. And from a static charger, we've assumed 100 kilowatt charging at depots and 600 kilowatt rapid charging at any drop-off stops or rest stops. So I now want to talk about the different charging scenarios and the journeys that we considered in this study. First up, the ERS scenarios. And here we considered 3 potential national ERS configurations, ranging from ERS Lite at around 2,800 kilometers of the network, up to ERS heavy, which is 8,500 kilometers of the road network. And these basically, ERS light covers the most heavily trafficked HGV freight routes in the country. And as we go to medium and heavy, they kind of cover your secondary, most trafficked routes, etc. In terms of our static charging scenarios, we've also considered 3 possible scenarios. The first up being our reference case of only having depot charging. So the vehicles charge up overnight, depart with a full battery in the morning, and do their entire day's journey on just that single battery charge. The second scenario is drop-off charging, whereby vehicles are able to take a 20-minute opportunity charge during any drop-off stop on their journey. And finally, we've considered a rest stop charging scenario, whereby vehicles are able to charge for over a 45-minute window during the driver's mandatory rest breaks after 4.5 hours of driving, again at 600 kilowatts. This brings me to the journeys we've considered. We've looked at 8 journeys in total, identified from a larger data set, and from this we've got 3 categories of journeys. So the first category is warehouse to warehouse operations, one example shown here, and a second example shown here between London and Worth-upon-Dearne. The second category of journeys is tramping journeys. Here's a 2-day tramping operation split into 2 distinct journeys. The first between Tyrrell, making several stops, and then an overnight at Wetherby. And the second part of this journey from Wetherby, several more stops before returning to Tyrrell. And the third category is multi-drop operations, and we see a few options here in the southeast and southwest of England, mainly from Aylesford. So one out here northeast, one out here to the east, another south from London, and then quite a challenging journey from Andover to various destinations in the east and the southwest. So in summary, we've got 8 trips across England, ranging from 300 to 700 kilometers and ranging from about 3.5 to 15 hours in duration. So this brings me to the results. I'll present these in a kind of bottom-up approach. So first we'll look at an individual drive cycle for an individual combination of charging scenarios, and I'll show you how that all works. We'll then look at a journey matrix, which is for a given journey, what do all the different combinations of static and ERS charging mean for the battery sizes. And then finally we'll look at the battery sizes over all journeys and scenarios and make some conclusions. So starting off on an individual drive cycle level, the example shown here is for the tramping day 1 journey with ERS light and with drop-off charging. What we see in the first plot is our drive cycle, so speed profile in black and our elevation profile in red. We can see the various stops, 4 20-minute stops along the journey, plus a 45-minute rest stop after around 4.5 hours of driving. And we can also see that in the grey shaded regions, these indicate where we have ERS available to the truck during this journey. Then running that through the vehicle model, what we then get is an output of what's happening with the journey. Importantly, what's happening with the battery dip profile throughout the journey, as it's either charged on static charging or ERS, or as it's discharged during journeys between any charging. We see here the static charging in red, ERS charging in blue at the different rates of 600 and 150 kilowatts. And the thing we're really interested in is this maximum battery dip, from which we can calculate using our estimated 80% state of charge range, usable state of charge range. We can calculate for this journey the minimum battery pack theoretically required would be 357 kilowatt hours. So moving one step up and looking at our journey matrix, what you see on the left here, for that same journey, we're able to look at each of the ERS and static charging scenarios and calculate the battery size required for each and create a table like this. So we've got our ERS topographies in the columns, none, light, medium, heavy, and the static charging options in the rows, none, drop-off, and rest stops. And the scenario we looked at in the previous slide was ERS light with drop-off charging, and we calculated 357 kilowatt hours. The journey we're looking at here is shown on the right. This is our tramping day one from Tyrrell down south and back up to Weatherby. So let's look at what the different scenarios mean for this journey. We have our reference scenario here with only depot charging. If we then add in ERS Lite, we can see that a large part of this journey is now covered by ERS, and so we see a substantial reduction in battery size. ERS Medium covers more of the journey, and ERS Heavy even more, leaving essentially just this part of the journey to be covered on battery alone, hence the significant reduction in battery size required. If we then look at the static charging scenarios, we have, for the drop-off charging case, 4 drop-off stops where the vehicle charges for 20 minutes at each one, and we have the rest stop charging scenario where there's only 1 rest stop in this case, and we can see still quite a large reduction in battery size. Of course, we then have all combinations of ERS and static charging, which we also assessed, and you can see the results there, but there's no need to go into that in more detail. What we will look at now, however, is we'd like to compare our pure ERS scenarios without any static charging versus our pure big battery with static charging options, which come from our first column here. So plotting all of those results across all of our journeys, we get the following plot. So in the left 3 columns we have our big battery plus static charging scenarios, and in the right 3 columns we have our purely ERS scenarios, ERS Light, Medium and Heavy. And we can make a number of interesting observations from this. Firstly, without any en route static or ERS charging, we see that battery sizes of up to about 1.5 megawatt hours would be required. It's quite substantial. We see that our most challenging journeys in this case come from our tramping and multi-drop operations as expected. And we see that for the rest stop scenario, the range of battery sizes is quite small. And this is expected because here the battery sizes are mainly dictated by the 4.5 hour driving window. And the variations are just due to changes in speed profile and elevation profile between the journeys. Looking then at the impact that ERS has on reducing battery sizes, for ERS Light we see about a 40% reduction in battery size. ERS Medium we see an additional 20% reduction. And at ERS Heavy we see an additional reduction, though with diminishing returns. But what we do see is that, some of these remaining big battery trips or big battery trucks have now been captured by the ERS, and so we're reducing the number of large battery trips that would be required on UK roads. So in summary, we can see quite a consistent effect that the ERS has across all the static charging scenarios. And broadly speaking, for ERS Light, we have a 40% reduction in battery sizes, 60% reduction at ERS Medium, and a 75% reduction at ERS Heavy. And if we consider some of the pricing we're seeing for some of the first generation battery electric trucks at around 40 tons, these savings would result in substantial cost savings and assist in the future uptake of electric trucks in the country. That then brings us to our conclusions. So in summary, we analysed 8 different real HGV journeys in the UK at 44 tonnes, and we analysed these against 12 different combinations of ERS and static charging. Across all journeys and static charging scenarios, we showed that for these journeys, ERS reduced battery sizes by 40, 60 and 75% depending on the ERS topography. This of course has significant implications for reducing vehicle cost, reducing vehicle weight, and reducing the embodied emissions and reliance on different resources associated with the manufacturing of those battery packs. In terms of the next steps, we're now looking at doing much larger scale simulations of many more journeys using a slightly simplified model. And in parallel with this, we will be looking at the economic implications of this battery size reduction and difference in charging infrastructure at a national scale. That brings me to the end. I'd like to thank you for your time, and please feel free to contact me if you'd like to learn more.